Okay, students. So now we have already discussed what relative atomic mass is. That is for atoms of elements. Now we are going to discuss relative molecular mass. So here you can see the symbol capital M and subscript R. That is how we denote relative molecular mass. Now let us look at the definition for that. How many times a given molecule of an element or a compound weighs as much as 1/12 the mass of carbon-12 isotope is the relative molecular mass of that element or compound. Now this part, starting from here up to this point, is the same. How many times a given molecule of an element or compound weighs as much as 1/12 the mass of carbon-12 isotope. What did we call that? It is the atomic mass unit. You can remember that. So here also we are going to calculate the relative molecular masses in relation to the atomic mass unit. But here we are going to calculate for both molecules of an element or a compound. I am sure you know the difference. Now, if we take molecules like oxygen, O2 molecule, or N2 molecule, or let's say hydrogen, H2 molecule. Now, these are all gases and they are elements. But these elements exist in the form of molecules. So, here molecule of elements. Molecule of elements. What is the special name given to these type of molecules? We call them homoatomic molecules. Homoatomic molecules. Then we say compound. Now let's say oxygen and hydrogen combine to form water. So this is a heteroatomic molecule. Heteroatomic molecule. And this is a compound. So when we consider the relative molecular mass, we need to consider both these types of molecules. That is why we define it as how many times a given molecule of an element or a compound weighs as much as 1/12 the mass of carbon-12 isotope is the relative molecular mass of that element or compound. Can you all understand that? So now we will write the equation. So how do we write? Relative molecular mass equals mass of a molecule of an element or a compound divided by the 1/12 mass of 12,6 carbon atom. So now you can understand the relationship. Only this part is different. So here, since it's relative molecular mass, we have to write molecule. So mass of a molecule of an element or a compound divided by 1/12 mass of 12,6 carbon atom. So that is the equation. So then you know what to do. We have to substitute the mass of a molecule here and we divide it by 1/12 the mass of 12,6 carbon atom. What is the unit? This is in grams. This is also in grams. So when you simplify, there is no unit for this relative molecular mass. So I can include that as well. There is no unit for relative molecular mass. Now we will look at some examples. The true mass of a carbon dioxide. So here you can see it is a molecule, and since it's a heteroatomic molecule, you know it's a compound, is 7.31 into 10 to the minus 23 grams. Mass of a carbon atom is 1.99 into 10 to the minus 23 grams. So we need to calculate the relative molecular mass. So always you have to write the equation first. Relative molecular mass. So here we can say mass of a molecule of carbon dioxide. That is divided by 112 mass of 12,6 carbon atom. Then what do you have to do? We have to substitute the values. So the mass of one molecule of carbon dioxide is 7.31 into 10 to the minus 23 grams. That has to be divided by 1 over 12 into, you know the value for this, 1.99 into 10 to the minus 23. That is also in grams. When we do the calculation, how do we do it? You can remember the gram and gram gets cancelled off. 10 to the minus 23, 10 to the minus 23 gets cancelled off. So the remaining values are 7.31 and you rearrange. So the 12 comes up divided by 1.99. If you calculate the value, you will get the answer as 44. That does not have a unit. So the relative molecular mass of carbon dioxide is 44. So did you all understand how to do the calculation? This is a direct substitution. You should remember the equation for relative molecular mass. Mass of a molecule of carbon dioxide divided by 1/12 mass of 12,6 carbon atom. So directly we substitute the values 7.31 into 10 to the minus 23 grams divided by 112 into 1.99 into 10 to the minus 23 grams. So the grams get cancelled off, 10 to the minus 23 gets cancelled off. I'm sure you are very good in maths, so you know what happens here. Then we rearrange 7.31 into 12 divided by 1.99. So if you simplify this equation, you will get the value as 44. With that, I will move on to another example. Mass of water molecule is this, 2.99 into 10 to the minus 23 grams. Atomic mass unit is 1.67 into 10 to the minus 24. You know this method as well. Find the relative molecular mass of water. So here, how do we write the equation? You can remember that we discussed this with relative atomic masses. Here also we write relative molecular mass equals mass of a molecule of a compound. You have to divide that by atomic mass unit. So here, instead of writing 1 over 12 into mass of 12,6 carbon atom, we write it as atomic mass unit. So that is the equation you have to use here. I will relate it to the question. So then we rewrite it again as, you don't have to write it twice. Here for you all to understand remember the equation and recall it, I wrote it once. Now I am going to do the calculation. So relative molecular mass of water is equal to mass of a water molecule divided by atomic mass unit. So then we substitute the values. That is equal to 2.99 into 10 to the minus 23 grams divided by 1.67 into 10 to the minus 24 grams. So again, the gram and gram will get cancelled off. You know what will happen to 10 to the minus 23 and 10 to the minus 24. When you simplify, there will be a 10 to the minus 1 there. So this is going to be equal to 2.99 divided by 1.67 into 10 to the minus 1. When you simplify that, it becomes 2.99 into 10 divided by 1.67. That will be equal to 18. That is the relative molecular mass of water. I am sure you can understand this as well. Just the second method. Mass of, so here to calculate relative molecular mass of water, mass of a water molecule divided by atomic mass unit. So here you substitute 2.99 into 10 to the minus 23 grams divided by the atomic mass unit value 1.67 into 10 to the minus 24 grams. So when you simplify, you will get the answer as 18, value 80. That is the relative molecular mass of water. With that, we will move on to the next one. If the molecular formula of an element or a compound is known. So here the molecular formula of an element or compound is known. Its relative molecular mass can be calculated. This is because the relative molecular mass is equal to the sum of relative atomic masses of the atoms in a molecule. This is something you have to remember, students. The sum of relative atomic masses. Now we calculated for carbon dioxide. I will take the same example. Now you know the chemical or molecular formula of carbon dioxide. Carbon dioxide, 1 carbon and 2 oxygens. So here, if you can remember, we calculated the relative molecular mass. So relative molecular mass was calculated as 44. We did it in the previous examples. So then, if we use the second method, Now, if the relative atomic masses are known, now say they give you the relative atomic masses, mass of carbon is 12 and oxygen is 16. This is there in the table in your textbook. For the first 20 elements, they have given the relative atomic masses. So then what do you do? For carbon dioxide, there is 1 carbon, so the relative atomic mass is 12. 12 into, you don't have to show the 1, I am showing it for the first time. Then for oxygen, the relative atomic mass is 16. Here you can see there are 2 oxygens. So we multiply this by 2. That means you will get the value as 12 plus 32. That is also 44. So the same value as this. Now do you all understand how to calculate the relative molecular masses if the relative atomic masses are known? You have to write the relative atomic mass of the atom of an element and multiply it by the number of atoms. Here there is only 1 atom, so we multiply by 1. CO2, there are 2 atoms, so we multiply it by 2. We will do another example. The similar one that we did before, we calculated the relative molecular mass for water. That is H2O, and we calculated it as 18. Now you know the molecular formula, H2O. And you know hydrogen has relative atomic mass 1. So then what do? We write 1 here, multiplied by 2, plus there is only 1 oxygen. So we write 60 and multiply that by 1. You don't have to multiply. As I said, for now I am showing you the value. 1 hydrogen, I will write it here. Relative atomic mass of hydrogen is 1, oxygen is 60. So we are using these 2 values. Hydrogen is 1, we multiply it by 2 because there are 2 hydrogen atoms. 1 oxygen, 16, we just multiply it by 1. So if you add them together, 2 plus 16, that is going to be 18. Can you remember we got the value as 18 before also? So that is how you calculate the values. We will do one more example. Let's consider ammonia. What is the chemical formula or molecular formula of ammonia? It is NH3. So, if you know the relative atomic masses, nitrogen is 14 and hydrogen is 1. So, how do we calculate for NH3? There is 1 nitrogen, so 14 is the relative atomic mass of nitrogen, 14 into 1. Plus what? Hydrogen, relative atomic mass 1, but there are 3 hydrogens. So, we multiply by 3. So, 14 plus 3, that will be equal to 17. So, the relative molecular mass of ammonia is 17. So, it is more easier than using the full normal basic equation, since we already know the relative atomic mass values. I am sure now you can understand both the methods. We will look at some more examples. relative molecular masses of some elements and compounds. So here you can see the first one, hydrogen. The species is given, molecular formula is given, and the way of calculating relative molecular mass is given to you. So the species, first one is hydrogen. Here molecular formula, you know it's H2. So hydrogen, the relative atomic mass is 1. But there are 2 hydrogens. So 2 times 1, 2. Then if we take nitrogen, the chemical formula or the molecular formula is N2. So N2, nitrogen is 14 atomic mass, relative atomic mass. So you multiply by 2, 2 into 14, 28. Then if we take oxygen, oxygen again is O2. So here you can see we multiply the relative atomic mass of oxygen by 2. Relative atomic mass of oxygen is 16. 16 multiplied by 2, you get the value 32. The fourth one, what we already calculated, carbon dioxide. So carbon dioxide, there is only 1 carbon, so 12. I told you, because it's the first time, I am showing the number 1. Just to show that you have to always consider the number of atoms. But once you are used to it, you don't have to multiply by 1. So 12 plus 2 times oxygen. So 16. Then you get the value as 44. Then we have the fifth one, glucose. I am sure you can remember the molecular formula of glucose. We have discussed this before. It's a monosaccharide, C6H12O6. So there are 6 carbons. 6 into 12. That is for carbon. Then there are 12 hydrogen. So this is for hydrogen. 12 times 1. Relative atomic mass of hydrogen is 1. Carbon is 12. Hydrogen 1. And this is for oxygen. That is 16. 6 oxygens are there. O6. So because of that, 6 times 16. When you add them together, 6 into 12, 72 plus 12 plus 96. You will get the value as 180. So that is how you calculate the relative molecular masses of some elements and compounds. Why some elements and compounds? These first 3, you can see they are all elements. These are the elements. And these 2 are the compounds. So that is why relative molecular mass can be calculated either for elements that exist as molecules or for compounds. So now can you all understand it clearly? I am sure you can. So we will do some more questions. Exercise 1. Calculate the relative molecular mass of the following compounds. This is the exercise from your textbook. So I am sure you can try it first. Then you can look at my calculation. The first molecule is ammonia. We have already done that also. So relative atomic masses are given to you. H is 1 and N 14. So for ammonia, if you are to calculate the relative molecular mass, then you have 1 nitrogen. So 14 plus you have 3 hydrogens. So 3 times 1. That is equal to 14 plus 3. That is 17. That is the relative molecular mass of ammonia. Then the next one, sulfuric acid, H2SO4. But students, you all have to remember the molecular formulae of different compounds. Compounds that are necessary for you for your syllabus. So you have to remember their molecular formula. Sulfuric acid, H2SO4. So relative atomic masses are given: hydrogen 1, oxygen 16, sulfur 32. So relative molecular mass of H2SO4, that is sulfuric acid. What is that going to be? There are 2 hydrogens. So 2 into relative atomic mass 1. With that, you have to add sulfur. Sulfur, you can see, is 32, and oxygen, the relative atomic mass is 16. But there are 4 oxygens. So 4 into 16. Here it will become 2 plus 32 plus 64. Then you get the value as 98. That is the relative molecular mass of sulfuric acid. I am sure you got the value correctly. So with that, I will move on to the next one. Sucrose, a disaccharide. You are familiar with that. So the relative molecular mass of, I can say, sucrose, or you can write the chemical formula C12H22O11. So if we calculate the relative molecular mass, the relative atomic masses are given to you. How many carbons? There are 12 carbons. What is the relative atomic mass? That is also 12. So 12 into 12. With that, there are 22 hydrogens. The relative atomic mass of hydrogen is 1. Then there are 11 oxygens. Relative atomic mass of oxygen is 16. So when you do the calculation, 12 into 12, 144 plus 22 plus you have 11 into 16, 176. So when you add 142, 22 and 176, you will get the value as 342. So that is the relative molecular mass of sucrose. So did you get the correct value? I am sure you all got it. So with that, I will move on to the next topic under the same relative molecular masses. Now here we calculated the relative molecular masses for molecules of compounds that are covalent compounds. But you know that there are ionic compounds in nature. Now we will see what they are. The ionic compounds such as sodium chloride exist as lattices, but not molecules. They are not in the form of molecules. So if we take a sodium chloride, now this is made up of sodium ion and chloride ion. Now what happens is these sodium ions, the positive ions and the negative ions can get arranged in 3-dimensional arrays like this. Alternately, they get arranged. So this is just the 2-dimensional arrangement. It will be a 3-dimensional. In front also there are ions, behind also there will be ions. So it's going to be a 3-dimensional lattice. So in this, you can see, unlike what we discussed before, if you take water, there are 2 hydrogens, 1 oxygen. But in this, there are so many positive ions, that's sodium ion, and negative ions, that's chloride ion. So in a lattice, there is going to be a lot of positive and negative ions. So what they do is they write the simplest ratio between the two ions. So the ratio between Na plus and Cl minus is 1:1. So then we write the formula as NaCl. If we calculate the relative molecular mass for this, then we call it as relative formula mass. So here we call this as the relative formula mass or formula mass. So if I read it again, its formula is written to indicate the simplest ratio in which the sodium and the chloride ions are present in the ionic lattice. This is the ionic lattice. In such compounds, what is calculated as the relative molecular mass is the mass relevant to their empirical formula. So what we write here is the empirical formula. So the relative molecular mass calculated for the empirical formula is known as the relative formula mass or formula mass of that ionic compound. So can you all understand what this is? This is different from the covalent compounds. They are ionic compounds. They exist as lattices, ionic lattices. Because of that, there is a ratio between the positive and negative ions. So we write the empirical formula giving the ratio between the ions. And the relative molecular mass calculated is known as relative formula mass or formula mass. Now we will do some examples. Relative atomic masses are given for both sodium and chlorine. So if you are to calculate for sodium chloride, the relative formula mass or formula mass is equal to, again there is one sodium. So you write it as 23 plus 1 chlorine, so 35.5. And when we add them together, we will get the value as 58.5. So here again, there is no unit. So relative atomic mass, relative molecular mass, and relative formula mass, all of them are relative terms and they don't have a unit. So here also it's 58.5. That is the formula mass or relative formula mass of sodium chloride. I'm sure you can understand this as well. There's no confusion, no? So now we will do some examples. Exercise 2. This is again the exercise from your textbook. Calculate the relative formula mass of the following compounds. So the first one is magnesium oxide, MgO. So here again students, you all know to write the chemical formula. So here it is the ratio between the ions. Magnesium oxide. Relative atomic masses are given to you. Oxygen 16, magnesium 24. So if we find the formula mass of magnesium oxide. You can write it in words or the empirical formula. So magnesium is 24, oxygen is 16. When you add them together, you get the value as 40. So that is a very simple calculation. I will move on to the next one. Calcium carbonate. So here also the formula mass or the relative formula mass of calcium carbonate. So what are the relative atomic masses? Carbon 12, oxygen 16 and calcium 40. So calcium 40 plus carbon, there's only 112 and plus there are 3 oxygens. So 3 times 60. When you add them together, plus 48, so that will be equal to 100. 40 plus 12, 3 into 16 is 48. So when you add them together, the relative formula mass of calcium carbonate is 100. Then the next question. Potassium sulfate, K2SO4. Relative atomic masses are given, oxygen 16, sulfur 32 and potassium 39. So relative formula mass of potassium sulfate. So that is equal to, first is potassium. How many potassium atoms are there? Actually here they are in the form of ions. There are 2. So 2 times 39. Plus we have 1 sulfur, so that is 32. And then there are 4 oxygens. So 4 times oxygen is 60. So then if we calculate 78 plus 32 plus 64. So this is going to be 174. 174 is the relative formula mass of potassium sulfate. Okay, students. So up to now, we have discussed how to calculate the relative atomic mass and relative molecular mass as well as the relative formula mass. So we started by defining the atomic mass unit. You have to remember that equation and the equations for relative atomic mass and relative molecular mass. And remember, there is no unit for relative atomic mass and relative molecular mass. So the next topic will be Avogadro constant and moles. So that will be discussed in the next chapter.